certain ideas in particle physics and beyond. And let's see. So, unification ideas. So, unification, what does it mean in a nutshell? It means finding connections between diverse phenomena and or objects, and in other words, a certain unity in diversity, and seeing oneness behind many, which is usually hidden to the common eye. And in fact, this is a very famous quote. This is represented by Einstein saying, nature hides her mysteries in her essential grandeur, not by cunning. Now, an accompanying quest to find this essential grandeur, that is actually the goal of physicists trying to search for fundamental laws of nature. And so the accompanying quest in this search is for beauty and simplicity in the underlying laws of nature. That actually has often provided the clue to such a unity. Maybe I will stand here. It might be slightly easier. These are familiar examples, but I should mention it anyway. The examples of Newton. The point is that it's not a new fall, but it's the fall of the apple and the motion of the planets. So the celestial and terrestrial forces which were not known to be the one and the same force, he recognized that it is one and the same force, and then the 1 over r square law. So that was actually quite an important realization. But notice, it is not a new force. It is one and the same force that he recognized is operating in different scales. The remaining ones are really something new things, different things are being connected together. And that is, for example, Maxwell unifying electricity and magnetism following the experiments of Faraday, Ampere and others. And he also added something to it. And that is some of the most beautiful parts of physics, Maxwell's equations. And he also realized the so-called universal speed of light. All electromagnetic waves are related by the difference in frequency or wavelength, and light is, visible light is part of that. Then came Einstein, a very big thing happened, which special theory of relativity, unified space and time, and got rid of the ugliness that laws of nature could possibly depend upon the inertial frame in which you are observing. So that really he was trying for beauty and got rid of that ugliness. So it is the same in all inertial frames. Then he extended it to accelerated frames, and that led to another major unification, that is the curvature of space and time, namely the geometry is what is giving rise to what we call gravitational force. It's not a force in the usual sense. And I will say more about this later. Then came quantum theory, which is not say much, but as you know, it tries to unify particles and waves, and also it gives the notion that indeterminacy, which is Heisenberg's uncertainty principle, can merge into determinism if they are not contradictory. They are limiting cases. And now the modern ideas are unified theories of fundamental particles and forces, and that's what more particularly I will discuss more. At a deeper level, the idea is there is one force and one type of matter, and that was actually Einstein's dream, though he didn't realize it. Now, as far as I can cover, I will just see, I will go and then see how far I could get there. But the idea is that at least whatever I cover, let's see if all of us kind of fully share and appreciate that If you have any questions, please do feel free to ask and raising your hands. Now, so in order to unify particles and forces, we need to know what are the building blocks, the quarks and electrons, what are the forces, the nuclear, electromagnetic, weak and gravity. We need to know what are the force carriers. Photon, you are familiar, is one of them. It mediates the electromagnetic force. And then we need to know about antimatter. We need to know something about spin. The very important part we need to know is the role of duty and simplicity, and that I will comment on. And here the idea of symmetry in the laws of nature plays a very basic role. And then comes part of the symmetry idea is the gauge symmetry, that is a special kind of symmetry which gives rise to gauge forces. Electromagnetism is one of them. And now the idea is the nuclear and the weak radioactive, they are all parts of gauge forces and they are all unified as aspects of one force. So I'll try to see if we can cover this much. Now on the bottom I give you this story building from bottom to the top. I call it the unification pyramid. It could be drawn better. But as you see, electromagnetism was done by Maxwell. Then electromagnetic and weak forces are linked. They're not really unified, which is a subtle difference. And but that idea developed during the 1960s, late 1960s, and then to it a fundamental force of color gauge force was added. That makes the standard model, and that is operative at a scale, energy scale of 100 GeV. Then came, in fact, the standard model didn't exist when the idea of grand unification came into existence. Only the electroweak unification existed. But the standard model with the color gauge force was not part of the thinking. I will come to that. But the so-called grand unified force is unify the electroweak and the strong nuclear force, the fundamental strong nuclear force which is the core gluon force. And finally, now we are in a stage where I'm just calling it string M theory, which is defined in 10 dimensions, and string theory in 10 dimensions. It attempts to unify all four. In fact, it has the scope to unify all the forces, including gravity and all matter, and probably give a good quantum theory of gravity, which we didn't have before string theory. But string theory is in a very preliminary stage. It's not properly understood, so it hasn't made contact with the real world yet. Now, I will skip this. We'll cover some of this. Now, before before proceeding further, let me draw your attention to something about which we ourselves should consider really fortunate. And that is the fact that all of us have really seen in our lifetime three spectacular discoveries during the last decade. Each was predicted long time ago by a major unification idea. One of them is the Higgs boson, which was discovered at LAC in 2012. It was the last missing part of the idea of electroweak unification, which developed almost 45 years ago, before 2012. And then you see it has these two detectors, CMS, in which Professor Arun Naik from here is very deeply involved, and then the Atlas, and the Higgs particle, proton-proton collision at 7 TeV center mass energy or 8 TeV gives rise to Higgs plus other things. The Higgs boson then decays to 2 gamma, 2 photons, and also many other channels, and its mass is around 125 GeV. Now it was predicted on the basis of a very beautiful unification idea. It really puts together so many things in a nice way. It changed the thinking, that the idea of spontaneous breaking of symmetry and the gauge unification of forces. I'm being very brief about this. I'll show you Maybe I will show you that first. Here is the Large Hadron Collider, the LHC, and this is the CMS detector. This is, as you know, in Geneva, CERN, but also covered in France. This big ring is going around, and this is the CMS detector. And I will only briefly mention all these. And this is the famous discovery of the Higgs particle in the channel in which the Higgs is decaying into 2 photons. But it is seen in many other channels, and the mass is about 125 GeV. Let's go back to the previous slide. The next to Higgs boson is in 2015. The gravitational wave was discovered by the LIGO detector. LIGO stands for Laser Interferometer Gravitational Observatory. And now we have Super LIGO. India is actually part of it, and that's a very good thing. But the LIGO discovered something spectacular. What happened? Oh, sorry. Yes. Yes. It consists of 2 laser interferometers. One. Let's go to the picture. This is the LIGO detector. One of them. As I said, there are 2 of them in the US. One in Livingston in Louisiana, another in Hanford in Washington State. They are about 1,860 miles apart. And each of these LIGO detectors is really a Michelson-Morley laser interferometer detector, the famous Michelson-Morley. So you see, these are the 2 arms, and here, suppose this is a laser beam going. This is a mirror at 45 degrees. That's like Michelson-Morley. It is splitting the beam. Part of it is reflected towards this one along this arm, and the other one is reflected from this mirror along this arm. These 2 arms are at right angles. These are the 2 arms. And then they come back here, and they go through, and then here they interfere with each other. If suppose their length is equal, and if the length changes by a little bit, then you will see it in the interference pattern over here, right? That's what Michelson-Morley were trying to do. So this is exactly the thing. And this Einstein, when he predicted the gravitational wave, he said, but forget it, it will never be seen, because it's so weak. But you see, one should never use the word never, because who knows the ingenuity of people. But anyway, it really is an ingenious experiment, and took about some 20 years to put it together. And so the thing is that gravitational wave is being caused of sufficient intensity. It's being caused by the merger of 2 black holes, some 1.5 billion light years away. 1.5 billion light years away from us. And it came to Earth, and over this detector it lasted for about 0.2 seconds. So it was fortunate. Actually, this was during a test trial that they saw it. This was not a real one, but they realized that this is really the real thing. And so the thing is that gravitational wave will stretch at a given time, will stretch anything with mass in one direction, but it will shrink simultaneously in the perpendicular direction, and vice versa. It will go back and forth. So this shrinking is only about 10 to the power minus 18 meters along this 4 kilometer. This is a 4 kilometer detector. The shrinking is only 10 to the power minus 18 meters, which is about 1,000th of the size of a proton. So that much of change in the arm, either stretching or shrinking, leads to an interference pattern, and this detector is sensitive enough to detect that. That very, very, see, interference is always very, very sensitive, but this is extra sensitive. And so, lo and behold, it was discovered in 2015 in both detectors that they are 1860 miles apart. That's the whole idea of having the two detectors, so that they can subtract the background out. Because the background, due to noise of a car going by or some other thing, it won't be the same in the two detectors. So they can easily subtract out the background, and then there remains the signal. They compare, and they really also verified that the signal in one of them, in the Livingston detector, arrived 0.7 millisecond, 0.7 millisecond before it arrived in the Hanover detector. And that's just about the time that you need anything with speed of light to travel from one to the other. So everything is all in good command. This precisely tests Einstein's general theory of relativity. And you can even tell the masses of the original black holes which try to merge, and then you can tell how much energy was released. There are 36 solar masses and 29 solar masses. They merge, but 3 solar masses are left, and that is emitted as energy as gravitational waves. And that's what you are seeing. You see, you needed that intense source, even though it is so far away, and such sensitive detector to see it. So this is a real demonstration of a unification idea. Unification due to Einstein of unifying the geometry of space-time with gravity. And you see, these are indeed these are ripples in space-time. Ripples in space-time. So this is what they were observed. Okay, so now let's go back to the third one, which is really the most spectacular one. And we are fortunate we are here to see it. This was very recent, the black hole discovery. This was done by the Event Horizon Telescope in 2019. Again, this was predicted by Einstein's general theory of relativity during 1915 to 1919. That is, Schwarzschild really said that you must have, the black hole solutions exist, which are singularities, mass coming to a point of singularity, and it will be surrounded by a horizon. And the horizons too, you could calculate for a spinless black hole. It's very, anyway, it was like 2 gm by c square. So m is the mass of the object. So the bigger the mass, the bigger the radius of this. Anything within that radius, which is called the event horizon, that sphere around the singularity is called the event horizon, and anything inside it will remain inside, cannot go out. So it will not even light. So that's the idea of a black hole, right? And the whole point is everything was really verified. And quite clearly, if you imagine, this is really the weirdest object you can ever imagine that could exist in the universe. And the fact that it could actually, Einstein and Schwarzschild said, such a solutions exist. But how would such a solution be realized in the whole history of the universe? The point is, Chandrasekhar actually opened the door for that. The gravitational collapse of stars, depending upon the mass, it will become a white dwarf, and the limiting mass is 1.4 times solar mass, or it will become, if it's higher in mass, about 2 to 3, it will become a neutron star, which was discovered by the pulsar around 1970 or so, 72, 73. And then the even bigger mass will become a black hole. And that collapsed. There is no way to stop it. So that was actually, the door was opened by Chandrasekhar. Then the refinement with neutron stars and black holes was done by Oppenheimer, Volkov, Snyder, and also Wheeler and others. And then the whole story slowly unfolded in the 60s. Nobody believed that black holes will exist. But lo and behold, this is a direct observation of a black hole, and they exist, likely to exist in the center of most galaxies, or all galaxies. In any case, this is truly another real test of a major unification idea in time. So let's proceed. This was just to show you that how unification ideas in different areas are working. The Higgs is in particle physics, the gravitational wave and the black hole is in space-time physics, and so this is the story. And oh, I forgot to show you the picture of the black hole, which you must have seen, right, all of you. So you notice this is the event horizon, and there is a reason why this side is brighter than this is. But and the radius goes quite well with the mass and so on. And there are 8 radio telescope detectors spread around the Earth in different parts. And these are the radio detectors in each place. And the reason for spreading it around is that effectively it increases the diameter of the telescope. And bigger the diameter, the smaller is the resolution, more better is the resolution. So this went on. Now let us go turn to particle physics and to the smaller and smaller constituents. And this will remind ourselves that the building blocks, namely, okay, I have to go a little bit. So we know about the protons and neutrons, and they are not elementary, they are made out of what are called quarks. And here is the up core, down core. Proton is made out of 2 up cores, 1 down core, and neutron, 2 down cores and 1 up core. So this is their spin, but these cores have fractional charges, like I put, and their sizes are now known to be less than actually 10 to the power minus 18 centimeters. So they may be the ultimate elementary building blocks, as far as we can tell. But all stable matter, you see, is made out of just these 2 things, up and down cores, and electron, 3 things, right? All stable matter. So that's a nice thing. But that changes very quickly, this economical picture, when in the 1950s they started discovering new particles, and now we have 3 families of cores and 3 families of leptons. See, this is up and down core making protons and neutrons, but there are charm and strange core which are heavier, and there are top and bottom core which are heavier. These are like just replicas of each other. So there are 3 families of cores, each having 2 members. And similarly, there are 3 families of leptons, which consist of electron and a neutrino. Of the electron type, neutrino of a muon type, neutrino of a tau type. And I hope you know what are the neutrinos. They are passing through us right now. Some 1 trillion neutrinos are passing through you and me per second through our body. They are coming from the sun, but of course harmless. And they are crucial. Without the neutrinos, the nuclear burning in the core of the sun won't work. And without that burning, sun won't radiate energy, or won't give heat and light, and we of course won't exist. So all these are crucial players in the whole cosmic drama. Including the neutrino. And let me maybe just mention it, I may not get time to explain this. There is some, already it is saying the neutrinos may be of the same kind as these objects, but there is something special about the neutrino, namely, even although the mass is increasing as you go from one family to the other, neutrino is in the same family, the top core. But you see, what I'm calling it name nu tau is misleading because the neutrinos mix and there are 3 eigenstates. But the main reason I put name nu tau is because whatever mass you get out of this hierarchical pattern, that actually essentially you can calculate within about factor of 3 corresponds to the mass of the heaviest one with hierarchical masses. So that's why I put for the sake of discussion. But you see this factor 10 to the power minus 12 is 1 part in a trillion. And therefore, there is something, this is some new physics is going on here as far as neutrinos are concerned. So please note this much. And that new physics was actually predicted, anticipated very precisely within beautiful unification idea of grand unification. And now let's continue. Then the course, another interesting part is that with each course comes in 3 different types. They are called attributes. And the physicists gave a very catchy name. These attributes were called radial or blue colors. They have nothing to do with radial or blue colors, but that's a good way of telling. But there are 3 different attributes, and they turn out to be crucial to generate the fundamental nuclear force, apart from the fact that they are also necessary to satisfy Pauli principle. When they are constituents of proton and neutron, they are really needed. But the most important part of this color degree of freedom is that it gives rise to the fundamental nuclear force, the gauge force. And the nuclear force that you see between proton and neutron is not that. It is induced by the fundamental color gauge force. And it's just like, you see, in the atoms we have charged particles, right? Protons and electrons. That force is fundamental electromagnetic force. But the molecules consisting of atoms, the atoms are electrically neutral. So those are effective forces between the different atoms. Fundamental force is the fundamental electromagnetic force. Likewise, color gluon force is the fundamental nuclear force. But that gives rise to the effective force between nucleons, neutrons, and protons by the exchange of what are called pi neutrons. Okay, so let's continue. And proton is made out of, this is one part I would like to draw attention. You remember I said proton is made of 2 up cores, 1 down core, but each one is of a different color, and you anti-symmetrize in the combination of radial or blue. You permute in an anti-symmetric manner. That's what the proton is. So proton is a color singlet object because it's a triplet of SU3 symmetry. I have not said what is SU3 symmetry for some of you not having any electric charge in case of an atom. Okay, so let's continue on. Finally, I have the 4 forces. The strong, electromagnetic, weak, and gravity, which, since I'm going faster, they are mediated by these forces, these particles. Like this one, you know, electromagnetic force is mediated by photon, but the strength is about 1/137. Compared to that, the strong force between protons and neutrons is of order 1, and quarks and gluons depend on the effective energy or momentum. But for rough discussions, let's call it order 1. But then the weak force is about 1,000 times weaker than electromagnetic force. And then the gravitational force is way too small for ordinary things between you and me or between the sun and the earth. The strength is really small. But near black holes become super strong. and that's what has given rise to black holes. And you see all four forces and all the particles I listed, even neutrinos, they seem to be crucial to the cosmic drama, including origin of life, so as if they are pre-designed. Now I will skip this. By the way, in the language of quantum theory, how does the electromagnetic force arise between an electron and a proton, or an electron and an electron? In the language of what is called quantum field theory, what happens is, you write it, they look like, those who study quantum mechanics, these look like the wave function, but they are really field operators. If I write a psi with a subscript electron, it can destroy an electron. If I psi bar, it will create an electron. Now in a moment I will tell you that each particle has its antiparticle, so electron will be associated with a positron with opposite charge but same mass. This same psi either destroy the electron or it can create its antiparticle, the positron. So let's remember this rule of the game, that the symbol, which looks like a wave function, is really an operator. It creates the particle or destroys the particle given by this symbol electron and creates its antiparticle. The A stands for photon field. It creates and destroys photon because photon is its own antiparticle. Now pictorially I can depict by this diagram. The electron is coming in, electron is going out. By this field here, electron is created by this, and the photon is either created or destroyed. But in second order perturbation theory, I can put this diagram together so that I exchange the photon. An electron comes in, and if the photon, this you will see, you can work out by ordinary kinematics that this will not be on what is called its mass cell, so it's a virtual photon, and it lives very short time by the uncertainty principle, and then it is absorbed by the other incoming electron. It is this exchange that gives rise, we can calculate it. We can calculate the Coulomb force out of this diagram, and you exactly get the potential to be E squared by R. So this is the fundamental electromagnetic interaction in the framework of quantum field theory. And it blossoms in this framework. All the interactions are described very effectively by means of quantum field theory. And the symmetries of the particles are also manifested beautifully in the framework of quantum field theory. So let's continue on. I am showing you the four forces and the corresponding exchange of the force carrier. Electromagnetic force is photon, weak force is the W particles. They have a mass of about 80 GeV. They are all spin 1 here. And the core gluon force, there are 8 gluons because there are 3 colors, and that those are all spin 1. But the gravitational force, I won't explain. It turns out the so-called graviton, which is the analog of the photon, actually has spin 2, but it also is massless, 0 mass. So it travels with the speed of light, and that is almost verified by the gravitational wave detector. It travels with the speed of light. And this, as I showed you, is the quantum field theory interaction. Let's continue on. I told you that it was first realized by Dirac that every particle, and in fact it becomes he only talked about spin 1 particle, but it's not, it extends to all the other particles. That each particle is accompanied by its antiparticle, which has the same mass as the corresponding particle, but all the charges are reversed. Electric charge, and there are other charges like baryon, so-called baryon charge, which is proton has a baryon charge of +1, neutron also is an important charge, and it is very well conserved as far as we know so far. And there is electron charge. So all these are reversed when you go from particle to the empty particle. Now all of these have been discovered with precisely the positron, antiproton, antineutron, and even antineutrino. So the idea of antimatter is very fundamental in particle physics. But if it is fundamental, you see, you and I and everything here, and even the distant galaxies, everything, are made out of just matter, up quark, down quark, and electrons. But the interactions of the strong and the electromagnetic force and so on, symmetrical between the matter and where did the antimatter go? How come we are not surrounded by antimatter, or at least nearby some antimatter? If there were, it's better that they are not here, because if they were there, what would happen? A particle will suppose be hit by an antiparticle, then they will destroy each other. They will give you photons. Quark and anti-quark will give photons and mesons. So we want this, right? In the early universe, particles and antiparticles were equal in number. For every electron, there is a positron. For every core of a given type, there is an anti-core. And there were some 10 to the power 80. Now there are some 10 to the power 83 or 85 photons around. Right here, about 400 photons per cubic centimeter in this room. So 400 photons per cubic centimeter. Similarly, there are up quark or protons and neutrons of that order, little bit less than the 10 orders of magnitude smaller actually, the level of proton. But question is, there are no antiprotons and there are no antineutrons. This is a major puzzle. It used to be a major puzzle. And actually you can calculate the number of quark minus the number of antiquark. This is 0 merely, the antiquark. So this is the same as the number of quarks divided by the number of photons. This is 1 part in 10 billion. This used to be a real puzzle. What caused this asymmetry, since they were equal at the time of Big Bang? Turns out the unification idea, which also explained the mass of the neutrino in a beautiful way, and neutrino finally, that people thought that neutrinos are exactly massless, but they turned out to have mass. And that same mechanism also can give rise to this asymmetry between quark and antiquark, and one can calculate and get this more or less this number correctly. So I won't have time to explain all this, but at least I should let you know that this is not a real puzzle. We still have to show that the mechanism we are talking about is correct. That's hard to do. But at least there are ideas, good, promising ideas. I will now turn to this question, which I have told you before in the beginning. That remember I said that the quest for unification, actually there is no set path, right? How do you know how to connect the different things? What's the guiding principle? There is no formula, there is no guiding path. It is entirely by human thought, human intuition. But what helps with that thought or intuition is often a sense of beauty and simplicity in the laws of nature. That has always prevailed to guide us from the day of Newton to arrive at some beautiful equation or a beautiful idea which then connects millions and millions of phenomena, millions of observations, and then one can test it. That's the way physics proceeds, fundamental physics proceeds. Now you see, talking of the spirit of beauty and simplicity, we all know that beauty is somehow, the concept is subjective, right? Somehow. But let me give you the thinking of some of the people. Some quote, Paul Dirac, the father of the famous Dirac equation and the idea of positron, antimatter, and so on. He said, many times he said things like this: a theory with mathematical beauty is more likely to be correct than an ugly one that fits some experiment. I have to emphasize this word some, and I will try to return to this point. Now, another time he says, it is more important to have beauty in one's equations than to have them fit experiments. Again, he means some experiments. Herman Weyl, this is a little extreme. My work has always tried to unite 2019 during a total solar eclipse. Because once you have total solar eclipse, then it is easier to see the deflection of the light, right, coming from a star, because that's very faint. And if the light of the sun is blocked completely by the moon, then you can detect the bending of the light. And Eddington is one of them in one of the groups. And then this was in 2019, and they really observed the bending of the light. And then overnight, it was of course highlighted in New York Times and everywhere. And overnight, he became the hero of the physics world. And he has remained the hero all his life, and is now. I think no one has surpassed. So the point is, one of the reporters came after this bending of light was measured, just fitting his prediction in the general theory of relativity. He asked, Professor Einstein, what should you have said if the observation didn't agree with your prediction? He responded, he touched his shoulder and said, he responded by saying, I would have felt sorry for the law, because the theory is right anyway. Now, you see, when you hear something like this, it's undoubtedly, these sound rather extreme. These people, you can't imagine that these people will sacrifice the truth for the sake of their own sense of beauty. You can't imagine that. So you have to interpret these statements. But it is true, however, that these statements have to show how theoretical physicists are often guided by pure intuitive thought of beauty. So though subjective, it often is proven to be right. Now let me try to explain briefly. I know my time is, I cannot, okay, let's see. Yes, we need to interpret these statements. And you remember I drew attention to the fact when Dirac said that fits some experiment. That in other words, it is more important to have beauty in the equations than some ugly facts which fit some experiments, ugly ideas that fit some experiments. Okay, let me illustrate what you mean, and interpret that, and you will see what I mean. What happens is, invariably, when the dust settles, some ideas are evolving, right? We are not clear, not everything is clear. There are some experiments in the beginning. But when the dust settles, through the sharpening of experiments and or theory, sometimes this has played an important role. I like to show you examples, and I have found it to be true